Okay, great. Yeah, so welcome to the second AI Fairness 360 community call or B. So this is the August 2022 edition. We already had the first call, the inaugural one on July 2022. So today we have a packed agenda. So first we will start off with a few announcements regarding the project. And then Samuel Hoffman will present a paper, and then I'll start to present a tutorial, but if we run out of time, we can always continue next time. And then we'll have some project updates, and then there will be some open discussions until the end of the hour, and then we'll close the call. Okay. So first, I ask Kush Varshni to make an announcement regarding the project. We cannot hear you.
Sorry. Yeah, so very quick announcement. So there's a well-known science summit that happens in Berlin every year, coinciding when the Berlin Wall fell back in 1989 in November. So they kind of seek out nominations for interesting scientific work, and then they select winners from that. So there were 1345 so 1,345 nominations this year to be honored, and they have several categories. So they have categories in life sciences, in physical sciences, engineering and technology, science and humanities, science, art and science, and then future learning. And then the last one, which is relevant for us, is science and innovation management. So it turns out that AI Fairness 360 was one of the 30 finalists in that category. And then just a few days ago, we found out that it was one of the 10 winners as well. So um, in that science and innovation management category. So this is a pretty nice honor for the project to be one of these winners. And you'll see other people like Robert Downey Jr., the famous actor on here, and some other really impressive projects that were part of the nominee list. So there will be one final breakthrough selected among these 10 that will be announced in September. And if that does happen, then the project would be kind of formally presented in Berlin in November as well. Okay. So I just wanted to make everyone aware that that this is a really nice honor for this open source project.
Thanks, Kush. Yeah, yeah, this is indeed a really big honor for all of us. So, I have one other announcement to make. So I think I probably mentioned it last time. Before we move to the paper, I want to also mention that so AI Fairness 360 is one of the projects to be featured projects in the Grace Hopper Open Source Day. So if you are all registered to the Grace Hopper celebration, consider joining the AI Fairness 360 featured project. So you can go to this website, anitab-org.github.io/open source day/featured, and you'll be able to see this is listed alphabetically, so you'll be able to see our project. So the goal of this is to improve the contribution of typically underrepresented communities like women in open source. So we have also three mentors. So two of them are here in the call, Sam and Manish, and there is also a couple more mentors, Anu and one more another mentors who is joining newly the team. So we'll all be in the on September 16th we'll all be available to like discuss the project, and also more importantly help newcomers contribute to the project. So right now we are curating a list of issues. So if you go to the issues page, so and you see this good first issue, so we are creating a list of these good first issues, and we are required to create about 30 of them at least before September 2nd. And and the people who will be on that day, They will be tackling these issues, and they'll be creating PRs, and we'll be helping them at least review the PR, if not merge them. We feel like this is a really nice opportunity for all of us to get involved. Like, so if any of you are registered, please join the open source day. And if you are already an expert user, we also have like more complex issues that you can, like take up and work on that day. And this is a great opportunity for all of us to improve the contribution of, improve the community engagement of the project. So that is my announcement. And now I'll ask Sam to present his paper. So his joint paper that he was going to present today.
All right, thanks, Karthi. Um, okay, so hi everybody. Thank you for joining this call. I'm going to be presenting some work that I did in the last year with some of my colleagues at IBM Research, as well as one of our interns from CMU, Michael Pfeffer. And in this work, we studied the application of ensemble techniques to bias mitigation. So the key problem that we identified was that often bias mitigation techniques are applied to small data sets, or generally they exhibit poor stability, high variance when deployed to data, and can often show this variance even when training on different subsets, just random subsets with different seeds. So things that appear fair on the training set may become, in fact, unfair when deployed. And so in a traditional machine learning scenario, one solution to this problem might be to look at ensembles of estimators, which have various advantages in that they can often improve accuracy overall, as well as decrease the variance and have other benefits like uncertainty estimation and so on. So given that ensembles are generally a good thing when it comes to performance or predictive performance, we wanted to investigate how they can be applied in the fairness space as well. So some of the tools that we used in these experiments were the LaLe open source auto machine learning toolkit. So this is an open source project from IBM, which helps us in various ways in automating the hyperparameter tuning as well as pipeline tuning. And it's compatible with all of the scikit-learn models, as well as most of the AI Fairness 360 algorithms and metrics. So it's a very convenient way to organize all of these different pipelines, which we're going to see later. So in this study, we gathered 13 data sets that are, many of them are found elsewhere in the fairness literature. Some of them are just taken from the UCI repository. And the goal here is not necessarily to gain insight into any specific data set, but we wanted to compile as many data sets as we could to draw more robust conclusions on average about the fairness ensembles. So there are a couple of attributes that we looked at concerning these data sets. So things like the number of features, the number of samples, the n calls and n rows, respectively, in this table, as well as the base level of disparate impact present in the training data itself. So not using any trained estimator, but just the outcomes present in the data itself. So we can divide the data, which will be relevant later, according to the size. So in this case, it's split greater than or less than 8,000 rows. but we could also look at splits based on disparate impact or number of features. So in the study, we wanted to look at a whole bunch of combinations of fairness mitigation techniques, as well as ensembling techniques to see which combinations prove the best in different scenarios and so on. So for the fairness mitigation, we used as many of the AIF360 algorithms as we could. The only real restriction there was that they have to be able to produce probability predictions, as these are used by many of the ensembling techniques like stacking. So that kind of brings me to the ensemble techniques that we use. So we tried bagging, boosting, voting, and stacking. And so these are all sort of meta techniques where they can be applied to many different estimator types. So voting and stacking can be applied to a heterogeneous set of estimators. So the difference there being voting, you train each of the estimators independently, and then they each make their prediction, and then you can either take a weighted average of those predictions or take the majority vote as the final prediction, whereas stacking, the set of predictions is then fed into a final estimator, which uses those predictions as features and makes the final prediction itself. So these can all be different types of estimators, or they could be the same type of estimator. Whereas in bagging and boosting, typically use the same type of estimator, but on a different training set. So bagging, you would take different random samples of the data, and in boosting, you would reweight the data based on whether the previous estimator made the predictions correctly or not. And then the final sort of layer of combinations that we looked at is estimator level or ensemble level type of mitigation. So estimator level, we would apply the mitigation independently to each estimator. So there would be n different mitigators as well as estimators, whereas in the ensemble level, the mitigation is only applied once and then fed to the entire ensemble. So for our experiments, we took a two-step procedure. In the first step, we trained the fairness algorithms by themselves in order to tune the best hyperparameters there. And then we applied those to each of the combinations I just showed you, running 5 trials of threefold cross-validation on each combination. And then we recorded all of the fairness and accuracy metrics for each trial fold. And we standardized these across data sets by scaling them to be between 0 and 1. And in this way, we can compare across data sets, even if those data sets have different base levels of disparate impact or ease of learning, different base levels of predictive performance that are possible. So the first question that we wanted to answer with all of this data is, do ensembles help in any way with fairness? So on the right, we can see a set of charts where we've done this scaling that I talked about, and then divided out the data by mitigation type, which is going to be the rows of charts. Each bar is going to be a type of ensembling. So the blue is no ensemble, orange is bagging, green is boosting, red is voting, and purple is stacking. And then this left column is going to show the standardized disparate impact outcome. So this is not directly interpretable as disparate impact since we did that scaling, but the idea is to show relative performance between the different ensemble techniques. And then the right shows the volatility of this disparate impact. And again, this is separately scaled, so it doesn't necessarily line up in terms of it's not interpretable directly as standard deviation, but again, it just shows a relative change in volatility. So the takeaways here are that ensembles can help with fairness, not without mitigation. So you do have to apply mitigation. Ensembles themselves don't improve fairness to much extent. But when there is mitigation, the main improvement is in volatility. So we see little to no improvement in overall fairness, but it can, the ensembling can help reduce the volatility, which we can see in the right, the set of charts on the right. So the second question that we wanted to answer, which is very similar, is do the ensembles help with predictive performance when there is fairness mitigation? So for this case, we looked at the F1 score and then did this similar scaling for each value. And the takeaways here are a little murkier, but in most cases, the mitigated ensembles can help either with performance outcome or volatility, but in general, it's very difficult to strictly improve both of them at the same time. So another outcome of this work was we compiled a guidance diagram, which you can see here, which is mostly useful for practitioners who may not have the sort of resources to run a huge combinatorial search like we did in order to find the best combination for their data set. So here we tried to provide some guidance as a quick starting point for which type of ensemble combinations work best for according to different data set attributes, which you can see here. So the input number of rows, is it greater than or less than 8,000? Is the base disparate impact greater than or less than 0.49? And then what is the ultimate target of this work? Is the most important metric fairness? Is it fairness volatility? Is it F1 score? Is it time? Is it memory? And it's important again to note here that it's not only optimizing for fairness without regarding anything else. We only considered combinations which were in the top third for both fairness and F1. So this would alleviate any issues where a model would be totally fair but completely useless performance-wise, or vice versa. So you can generally assume that the best fairness would still have decent predictive accuracy. And yeah, so in summary, we've the main outcomes of this work are that we explored how ensemble learning can help with algorithmic fairness generalization, and we found that it does improve fairness volatility in certain circumstances, and we've recommended certain best practices in our paper, which are informed by our data. We also open sourced the code that we used, and it's present in the LALE toolkit. And we produced this guidance diagram to help practitioners avoid wasting time. So I think, yep, that's all my slides here. If there are any questions, I'd be happy to answer them. I think I saw one in the chat. Let me just open it quickly. Okay, yeah, so Jeff just asked, what does mitigation mean? So in this case, we average over, I think it was in this slide. So here we're averaging over all of the AIF360 algorithms that we used in the pre-processing mitigation row. And then the same thing, we tried all of the different in-processing algorithms in AIF360 and then averaged them and post-processing as well. So these are just the AIF360 algorithms that we're running.
Great. That's really great, Sam. Thank you so much. Any questions for Sam before we move on to the next agenda item?
I had a question. So
Sure.
in terms of the effect, I don't know if you can speak to ensemble models versus just making a more diverse data set in terms of making an algorithm fairer. Like, is it possible to speak of, like, what if you just improve the data set? Like, how much more effective is that?
Yeah, so we are able to, well, so it's a little difficult. We didn't run any sort of experiments where we reduced the number of training samples, but we could look at, say, the larger data sets in this, in our curated set compared to the smaller data sets. But I think in general, it's always helpful to compile more data to have a larger data set and so on. I think, yeah, it's not something we explicitly looked at, but I think it's pretty intuitive to me that collecting more data is always better. But the idea here was more to look at whether, given the data that we have, how can we best utilize it with ensembles. Okay, so there's another question from Han Lee. Is there a guidance on how to explain why the mitigation works, not explaining the prediction, as the ensemble complicates the modeling structure? I think I'm trying to interpret the question here. So the ensemble can complicate the structure, I suppose, but I think it's also pretty, at least like the voting is fairly intuitive, interpretable, I think, to me. Yeah, I'm not sure really, I guess, how to answer the question. I think it definitely depends on the mitigator type, how interpretable the process would be, but you can, for like voting, for example, you could certainly look at what percentage of the ensembles agree with each other. Yeah, it's the interpretability is not really something that we looked into, but it's definitely an interesting direction for research.
Yep. Okay. Any more questions? Okay. Thank you so much, Sam. So we can move on to the next item in the agenda. But I also want to mention one thing before we go further. So feel free to sign up to, like talk about your experiences with the toolkit, or whatever experiments that you have done that you may want to present, whatever pain points that you have. So it need not be in the same format that we have now. So we can also have some user experiences and all that, so we can have more open discussions about what are the things we can improve, or what is your experience, and so on. So feel free to sign up for all that. So let's use the Slack channel to discuss more about this. And so yeah, that is one thing I want to mention. So it need not be just like presentation of research paper, some tutorial, and the same format every time. It can also be more open discussions about your own experiences. Okay, so yeah. Yeah, having said all that, I just want to, we'll share the link to the Slack. So, okay, yeah, we'll definitely do. Um, so I think there is let me actually point to this page. So if you go to AIF360.mybluemix.net, I think there is a community tab here. So the community Slack page is here. And I think if you click here, you will get an invitation if this still works. Okay, seems to work. So it says launching AIF360. So yeah, that should help, I think. Just go to AIF360.mybluemix.net/community and you will be able to join the Slack channel. Okay. So yeah, so now I'll start presenting this. I'll go for like 15 minutes in the interest of time because we have other agenda items. But if there is more to cover, we can always continue next time. So the goal here is to introduce two things to the group. One is this algorithm called multidimensional subset scan, and the other is how to create a data set in AIF-NS 360. So as you know, AIF-NS 360 has two two types of ways to create data sets, and two types of bias mitigation algorithms and so on from a software standpoint. One is the more classic way of like doing things using AIF360's own data set structure and stuff like that. The second one is using pandas data frames and scikit-learn compatible AIF-NS360. So here, since many of the algorithms are still available in the classic version, which uses an AIF-NS360 dataset, I'll show how to create an AIF-NS 360 dataset for this particular application, and also how to use this subset scanning method. Okay, so the application here is a very interesting one. So this is something some of our colleagues we did recently. So you can so this is it is to discover, measure, and mitigate bias in advertising. So in advertising, what happens is when you have these targeted advertisements, so you have like a targeted user that's described based on some attributes, and you provide the advertisement to the user, you present it to the user, and depending on whether they click or not, you decide whether they converted or not. So if somebody clicked an advertisement, it means that they have converted, and if someone did not click the advertisement, it means they did not convert, right? So and this is written with bias because so the targeted audience could be very biased based on whatever algorithm that is deciding to target the audience, right? So the question here is, how do you understand what bias is there, and how do you measure and mitigate bias using AIF-NS 360? Okay, so that is the use case. Okay, so the description of the use case is provided in a lot of detail here, but basically the idea is what I just mentioned. So and this targeting data is collected in a data set, and usually it has feature attributes such as gender, age, income, political, religious affiliation, parental status, home ownership, area, and education status. So this is a data set that we collected with our partners at IBM, and we have posted this publicly. So this is an open data set right now, so you can use it and play with it and so on. And this notebook is also available in AIF Fairness 360. I'll point to that at some time. So these are the attributes of the user. So along with these attributes, you also have a predicted probability of conversion and the binary predicted conversion, which is obtained by thresholding the predicted probability. Okay. So these are predicted by the algorithm. So all these two are predicted by the algorithm. But in addition, you also know for this data set whether the user actually converted or not. So you have a true conversion as well. So a user is converted to have considered to have converted if the true conversion is 1, and this happens only if they click the ad. Okay, so I hope this is clear, but if you have questions, let me know. So all this data is run through this data is collected during a campaign, and we have actually collected all this a whole bunch of this data, and we have provided the open data set. So now what we want to do is to actually use the AIF-Fairness 360 toolkit and particularly the multidimensional subset scan method in the toolkit to discover the groups. The groups are determined by a subset of these attributes, the demographic attributes. So we want to discover groups that exhibit high predictive bias. So what does high predictive bias mean? So if the actual conversions are if the predicted conversions are small and if the actual conversions are large, then this particular group is said to have high predictive bias. So now the problem is, since these are, say for example, you have like 10 attributes, right? So if you want to do this manually, it's a combinatorial problem, right? Because you have to consider each combination of these groups, and you need to check what the predictive bias in each of these groups is. But we have this multidimensional subset scan method which can do it automatically. So that is the first step, right? So once you determine these groups that have high predictive bias, you can actually use AIF-Fairness 360 to mitigate this bias. So that is the second step. Okay. So after you get the subgroups, you use AIF-Fairness 360 to mitigate the bias. And this is all using the open source tools that we already have in the toolkit. So the group with the highest predictive bias is designated as privileged, and rest of the group records belong to unprivileged. So usually when we say privileged and unprivileged, we refer to socioeconomic privilege. But in this particular application, it just depends on the predictive bias. Okay. So that is the main difference in terms of the terminology between this application and other applications. So for bias mitigation, we use the reject option classifier method, but I don't believe we will get to that today. We'll probably go maybe up to half of the notebook, and we can continue the rest next time. So the notebook has a lot of details on how to install and like AIF360 and how to obtain the subgroups and compute bias and mitigate bias. So these are the steps that are performed in the notebook. The first step is to actually import all the libraries that we have. So we have pandas, numpy, and stuff like that, and we also have AIF-Fairness 360 data sets. So as I said, this particular notebook uses the more classic version of the data set. So that's why we are using the standard data set and so on. And it's also using the classic version of metrics. So we import the classification metric and the binary label dataset metric. The scikit-learn versions do not have these abstractions. They have different abstractions. So, and in order for the post-processing bias mitigation, we use reject option classification. Okay. So the first step is to load this dataset. So the dataset is available here. So if you click this link, you have this bias and advertising dataset, which is available openly in developer.ibm.com. So you can get this dataset, and you can place the dataset in the same location as this notebook whenever you run this notebook. Okay. And the name of the dataset is ad campaign data. So this is how the dataset looks like. So it has religion, politics, college educated, yes or no, parents, yes or no, homeowner, yes or no, gender, age, income, area, true conversion, predicted conversion, and predicted probability of conversion. Okay. So so the predicted conversion is obtained by thresholding the predicted probability at a certain level. Here it is 0.365, And the threshold is determined so that you have similar number of true conversions and predicted conversions. So that's how the threshold is determined. So the machine learning model that targets users is only going to provide the predicted probability, and it uses all these features to obtain the predicted probability. And the true conversion is obtained after we finish the campaign, because that's when we'll know if somebody has truly converted or not. So one of the interesting features of this data set is that it has a lot of instances. So you can see that it has 1.4 million instances and 12 features. And the other main characteristic is that the number of true conversions is very, very small. It's like 0.01%. Okay. So it's not, so usually like, so this is a very imbalanced data set. So, so that is another challenge with this data set. Okay. So yeah, so there are 1.4 million rows with only 2,300 true and predicted conversions. Now we want to determine, so since this is such an imbalanced data set, we also want to determine which groups have highest predictive bias. As I said, so we use this subset scanning method to do this, since brute force approach will be computationally expensive, as there are exponentially many subsets to investigate. Okay. So now before we actually do the subset scanning, we want to randomly pick a subset and we want to show what the predictive bias is, right? So the question we ask is, how do the true and the predicted click vary for randomly selected subsets? Okay. So so let's choose some, and this is a utility function that does that. So let's choose some randomly selected subset with some random seed. Let's choose a subset, and the subset is politics is unknown and religion is other. So the feature is politics, and the feature value is unknown, and the religion is other, right? So now the subset set is subset size is 214,000, and number of true clicks is 357, and the number of predicted clicks is 376. So you can see that this group has pretty much similar number of true and predicted conversions. So there is not a lot of predictive bias, right? Now, how do you, so if you keep searching like this, you will end up doing a lot of searches, right? So you won't know which group has the most differentiated true and predicted clicks, right? So that's why we use bias scan. So if you use bias scan using a simple procedure, you'll be able to, and this is also very fast. So using a simple procedure, you'll be able to obtain the subset that has the most predictive bias. Okay, maybe I shouldn't have run that, but yeah, no. So the true clicks is 281 and the predicted clicks is 1907. So this group has a high predictive bias because the model predicts that their number of clicks will be 1907, but the number of true clicks is actually only 281, right? And the model also, the subset scan method also provides the subset that leads to this high predictive bias and the size of the subset. So in order for us to use this with AIF360, we simplify the subset. Now we say that there are the subset that we want to choose is people who don't own a home, that have so the subset that the bias scan procedure provides is people who don't own a home, who have greater than 100K income or unknown income, and who live in an urban area or an unknown area. And unknown is basically saying that, you know, when they collected this data, they don't know what the area is, right? It's not, they don't know whether it is urban or rural. So that's what unknown means. Now we simplify the subset and say that, okay, let's look at subsets that have homeowner, that of people who are not homeowners and who are homeowners, right? Now, if you do that, you still get high predictive bias for not homeowners, right? So the true clicks is 332 and the predicted clicks is 1944. And for people who are homeowners, the true click is the bias is in the other direction, and the predicted click is 423. Now, from this scan, it is evident that people who don't own a home constitute a group, right? We call this the privileged group because the model actually predicts that you know, like you should serve a lot of ads to them because they will click a lot. So that's why we call it privileged, but they actually click only less, right? So so there is a huge gap between what they actually do and what the model predicts. And the model is providing a lot of advantage to them because it's serving a lot of ads to them, right? Assuming that getting a lot of ads is actually a beneficial outcome, right? So this is our data. So this is how we are going to divide this data set into two groups: people who don't own a home and people who own a home, right? Now, in order for us to take the CSV file and convert it into a dataset format that AIF360 can use, we have a utility function here, right? And this is the last thing I'm going to say here today, because the rest of the stuff we can discuss next time. So what happens is, so when we use AIF360 and the classic dataset format, we actually have this standard dataset function, which takes a data frame and converts it into a standard dataset format that can be used by AIF360 methods, right? So in order for that to happen, you need to specify what the protected attribute is. Here we specify that it's the homeowner. We need to select the features that need to be in the dataset. Here we say that it's gender, age, income, area, college educated, homeowner, parents, and predicted probability. And we need to say what the privilege class for the protected attributes are. So, here the privilege class is 0 because we are going to look at people who don't own a home. We also need to say what the favorable target label is. So here the favorable label that we consider is getting served an ad, right? So the favorable target label is 1. And we also want to say what the categorical features are. So these are the categorical features that we specify. So after that, it's just this simple call to this method that's going to take this data frame and create a standard data set. So standard data set is a base class for every binary label data set. And it contains a pre-processing routine. So this standard data set already contains a pre-processing routine that does a bunch of stuff, such as renaming columns, dropping unrequested columns, dropping row with NA values, creating one-hot encoding of categorical variables, and mapping protected attributes to binary 1-0 values, and mapping labels to binary 1-0 values. So all this is done by this standard dataset call here. So now we'll call this function that wraps this standard dataset object and creates a standard dataset. So this is the standard dataset that we get from this add conversion dataset, where we provide the target label and that names of the scores. So yeah, so that's I'll stop here, and next time we'll look at how to compute fairness metrics on this data set, how to mitigate bias, and how to check if the mitigation actually worked. So any questions before we go to the quick updates that we have from Sam? Maybe I'll take 1 or 2 questions, and rest we can discuss in the Slack channel. Okay. Yeah. Yeah, I mean, next time I'll recap a little bit of this, and I can finish the notebook. And if you have any questions at that point, I'm happy to answer. Sam, would you like to take over and provide an update?
Yep, sure. Yeah, so since the last month, we've had a number of pull requests, a bunch of updates to the R API, a couple bug fixes, some changes to the algorithms, namely the reject option classification. We've added support for probability predictions from there. There's a PR for improving the compatibility with FairLearn, including the threshold optimizer class from FairLearn. We are in the process of adding compatibility with an individual fairness set of algorithms called InFairness, which should be coming soon. And yeah, we're still awaiting some updates for the website. In terms of some of the metrics on the right, mostly the number of issues and the number of pull requests have gone up. So that's something that we need to work through. And we're also going to be adding some more issues, as Karthi mentioned, for the Grace Hopper convention. The roadmap looks about the same as last month. We're still have a couple things to work through for version 1.0, but the list is growing somewhat smaller. I think we still have a backlog of some things that would be nice to have. But hopefully some of these things we'll be working through in the coming month, as well as at the open source day. Yeah, oh, and then we already made these announcements. But yeah, just again, the open source day is September 16th. So hopefully we'll see some of you there. But yeah, that's all my updates for this month. Not too much has happened since last month, but some exciting stuff coming down the road.
Okay, great. Thank you, Sam. Any open things that anyone want to discuss? We have 10 more minutes. Anything that the community wants to say, or something that we should be doing better, or something that's going well? Any comments, questions, whatever?
I had a question about the Grace Hopper thing. So, how will that exactly play out? So will folks be just choosing issues on their own, or what will exactly happen?
Yeah, so if you are already registered to Grace Hopper celebration, you can also register to participate in the open source day. And during that time, they will ask which projects they are interested to participate in. And we have given them, an upper limit on how many people we can handle during that day. So they will admit people accordingly and assign them to projects. So once it is done, on that day, what will happen is we'll be assigned a Zoom room with breakout rooms and all that. So they'll be working through issues. They'll probably pick and choose issues, and we have to help them, and we'll assign them to issues since it's all happening through GitHub anyway. So we'll assign them to issues, and they'll be working through issues through the whole day, and we'll be there helping them out. And after everything is done, at least by the end of the day, they'll probably get some, like review comments and stuff like that. So it's going to be like somewhat of an informal thing. So I'm guessing people will be coming in and out, and we'll also be some may choose to work as teams. So we'll have like breakout rooms and stuff like that. That's my understanding so far.
Sure. Thanks.
Sorry, I have a question here.
Yeah, go ahead,
Can
please.
you hear? Yeah. If we want, are you open to integrating research from other people in your projects? For example, like let's say that we're working in fairness in my institute. Are you interested for us to open a pull request at some point with an implementation maybe of our research?
Yes, Sam, go ahead.
Oh, yeah, man, I was just gonna say, yeah, definitely. We're always interested in any sort of pull requests that we get. It yeah, it kind of depends on what state the code is, how much work you want to put into compatibility and so on. But I think, yeah, an initial step is just to get the ball rolling, and then we can chat on GitHub or on Slack or wherever to get it merged and so on.
Okay.
Yeah, and there's many examples. So researchers from EPFL in Lausanne in Switzerland, from the University of Maryland, Baltimore County, several others have contributed. So they've kind of developed their particular algorithms as part of their research and then contributed them. So there's a track record of that happening.
Okay, thank you very much.
So there was this comment in the chat by Surabhi. So would you mind telling us a little bit more about your research and kind of like how AI Fairness 360 is helping you? It would be good to hear for everyone. Just, I mean, how you're using it and what it's being used for.
Sure. Thank you so much. I'm Surbi and I'm working at the University of Rhode Island. Basically, I'm a graduate student, and my work basically focuses on ethical AI. And so we have been working on the technique to build a fair and how to basically select fair and relevant features from your data, because so far we have a lot of techniques to select relevant features, but there's nothing to select relevant and fair features, which is basically model agnostic. So that is what I am basically working on along with my advisor. And yeah, so in order to test our subsets, we are using the prejudice remover classifiers and other in processing classifiers to test the subsets. So yeah, in that way, it is really helping. Also, before we did the first part of our research, wherein we were actually looking at the variables having mutual dependencies with the protected attributes. And we did use the concepts involved in AIF360, and the whole research is basically based on a lot of functionalities of AIF360. So that way it's helping us a lot. And we did publish a paper uh, with our first research. But now that we are moving on to the extension, we are hoping to publish another one. So that way it's really serving us a lot, and it's very helpful. So yeah.
Excellent. Thanks for sharing. Yeah.
Thanks.
Okay, thanks a lot. Any final thoughts, comments? And feel free to join the Slack channel. Don't be shy, open a discussion. And even if you want us to do, us all to like do something new or something different in the next B, please provide your thoughts and we can work something out together. Okay, thank you so much. Thanks everyone for joining the call. See you next month. Bye.